Shapes of molecules. We're recording the lecture for those people who aren't here. We got to go through here kind of fast like because we got a lot of stuff to cover. This is important to pay attention to because this is stuff that's easy, I think, but you want to make sure you master it right away. No matter which chemistry class you were in last year, you guys did see this to some extent. We're going to be looking at more advanced structures this year and shapes you guys were not exposed to previously. Okay? Yeah. So when I say shape, this is like a less technical way of saying geometry, or I rather say a more sophisticated way of saying shape is molecular geometry. If you're answering questions on the AP test and you want to sound smart, use words like molecular geometry instead of shape. Makes you sound smart. Okay. Now, the way we're going to predict geometries is using this technical thing called the valence shell electron pair repulsion theory, which is abbreviated VS-EPR. And here is the guiding principle. Electrons all have what kind of charge? Negative, right? Which means they're going to do what to each other? They're going to repel each other, okay? Right? And the idea is they want to be as far away from each other as they possibly can. So we're going to apply this theory to describing the shapes of atoms, or of molecules rather, that have a distinct central atom. What's the shape of an atom? Spherical, okay? Now here's the idea. Bonding pairs of electrons and non-bonding pairs of electrons want to distribute themselves across the sphere so as to be as far away from each other as they possibly can, so as to minimize the repulsion between them. And that is what's going to give us the shape of the molecules. The fact that the electrons repel each other and get as far away from each other as they can. Does that make sense? Okay. So that's the whole guiding light, okay? Now we're going to make two distinctions, okay? The shape of the overall molecule is determined by where the electrons are at and how they arrange themselves. This is called electron pair geometry. This is how the arrangement of the electron pairs around the central atom, okay? And it depends on the number of what we call effective electron pairs, which I'll expand upon here momentarily. Once we know what the electron pair geometry is, how these guys are distributed across the central atom, then we can figure out what the geometry of the molecule is. When I say molecular geometry, what this means is really the arrangement of the atoms in space around the central atom, okay? Around the central atom in the molecule, okay? This depends on the arrangement of electrons. Does that distinction make sense? So we're talking about shapes. We're really talking about two shapes. The shapes the electrons make and the shape that the atoms make, okay? Now, what do I mean by effective electron pairs? Okay, well, here's what I mean. If I look at this molecule here, methane, it's got 4 bonds attaching the hydrogens to the central carbon, right? You guys would agree with me there, right? Each of these bonds here is how many electrons? It's 2. It's 1 pair, right? Each of these single bonds counts as 1 effective electron pair. So a single bond counts as an effective electron pair. If I look at this guy here, ammonia, NH3, which has this Lewis structure. You guys see it has 3 bonds, right? Each bond is an electron pair, and here we have a non-bonding pair, okay? The single bonds each count as an effective pair of electrons. A non-bonding pair counts as an effective pair of electrons. How many effective pairs does this have? 4, okay? If we look at carbon dioxide, how many electron pairs does it have around the central atom? 4. It has 4 electron pairs, but here's the trick, okay? For purposes of structure determination only, okay? If you have a multiple bond, like a double or a triple bond, they count as 1 effective pair. We treat them just like they were a single bond for the purpose of determining the shape. So this molecule here, how many effective pairs are around the central carbon? Just 2. Okay, does that make sense? Okay? So here we go. Now, we're going to go through here and we're going to look at some of the basic shapes that we can get based on the number of effective electron pairs, and then we're going to go on and look at ones that are more complex, okay? Here's the common geometries. Let's just get right into them, okay? The first and most basic is a linear molecule. You're going to get a linear arrangement of electrons if you have 2 effective pairs of electrons, okay? And the example that it gives here on this slide that I stole out of the next edition of your guys' textbook this is beryllium fluoride. Now, this is kind of a weird molecule because where's beryllium on the periodic table? It's where? in group 2, right? Which means it is a what? It's an alkaline earth metal, right? So you would not expect it to form. By the way, these shapes, these only apply to covalent compounds. What kind of bond would you expect beryllium to form with fluorine? You would expect it to be ionic. So this is kind of bizarro, but it is in fact true that it will form a quasi-covalent bond, whatever, with fluorine. Yeah, sort of. Don't worry about it. Just accept that this happens, okay? Here's my Lewis structure. So you guys can see, and this is also kind of strange because beryllium here is violating the octet rule. This just breaks the rules. It's terrible, but it happens, okay? How many effective pairs of electrons that guy got? 2, okay? So here's what this is going to describe. Because there are 2 effective pairs of electrons, we're to define 2 geometries, 2 shapes. The electron pair geometry of this molecule is linear. The molecular geometry is also linear because we have 2 atoms attached to the electron pairs. Now, in practice, you're not going to see something like this very often because this is El Strangio, right? But let's take a look at something else you are more likely to see. Let's consider carbon dioxide for a moment, okay? Like we just saw. We said a moment ago, how many effective pairs of electrons are on the central carbon? It's got 2. Because these double bonds here only count as 1 effective electron pair apiece. It has 2 effective pairs total. That means this is also going to adopt a linear electron pair arrangement and a linear molecular geometry. Does that make sense? Lightweight? No, they're not. And you'll see what I mean. Okay. Let's take a look at another one. This is the next most basic shape called trigonal planar. Did you guys see this last year? Maybe? Okay. So the example of a trigonal planar molecule, the best example I can think of is boron trifluoride, BF3. Now, what is weird about boron? And it's not triple bonds. What? There's an exception to the octet rule. Boron can be happy with fewer than 8 valence electrons. So if I draw the Lewis structure for BF3, it looks like this. I got a boron, bond to fluorine, bond to fluorine, bond to fluorine, like that, dot, 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 dot. How many electron pairs, effective electron pairs, are around the central atom? How many pairs? 3. So I have 3 effective pairs, okay, in this molecule. And that's what leads to a trigonal planar electron pair geometry. Okay, so I'm gonna write this down here. If I look at the arrangement of the electrons, the electron pair geometry, okay, is going to be trigonal planar, as will the molecular geometry, okay? Now, the reason why it adopts this shape is because, remember here, these electrons here that are around the central atom want to be as far away from each other as possible. They repel each other. And so they're going to try to minimize their repulsion by spreading out as much as possible. In 3 dimensions, the farthest apart that these guys can be is 120 degrees separated in space. That is the entire reason why it adopts this shape. Does that make sense? Okay, now Nasser here asked me a very good question. Well, are the electron pair geometries and the molecular geometries always going to be the same? And the answer to that question is no. Let's just consider here, for the sake of example, for the sake of argument, we have some element X, okay, which is bonded to 2 fluorines in much the same way, but it has a lone pair of electrons up there instead of a third bond. How many effective electron pairs does this guy have? It has 2, 3, because the lone pair of electrons here also counts as an effective pair for purpose of shape determination. And so this guy here also occupies space. It also is repelling the bonding electrons. And so the electron pair is going to be 120 degrees separated in space, but you guys see we're missing a third atom up here. So this will have an electron pair arrangement that is trigonal planar, but the molecular geometry will not be trigonal planar. It'll be a distorted shape, which we'll talk more about later. Does that make sense? So the electron pair geometry and the molecular geometry are not necessarily the same. Jared Gruber.
So you're saying that because of the electron pushing away, it makes the maximum distance between each thing?
Yeah, they get as far away from each other as they can because they repel each other.
Why is that molecule?
We are going to talk about that. Okay. The next basic shape is tetrahedral. You get a tetrahedral arrangement of electrons if you have 4 effective pairs. Okay? Now, The basic example of a tetrahedral molecule always that's used is methane, which has this Lewis structure right here, okay? CH4. Now, if you look at this molecule on the screen, this looks flat and two-dimensional. What does it look like the angle is here between these bonds? It looks like it's 90 degrees, but that is in fact not the way it is in three-dimensional space. Because in three-dimensional space, those electrons are trying to get as far away from each other as they possibly can. Here, I'm going to show you guys a model really quick. Here is a tetrahedral molecule. Yeah. You guys have all seen those before, right? This bond angle between these electron pairs is 109.5 degrees. That is something you guys need to know. For a perfect tetrahedral molecule, the farthest away these guys can be from each other in space is 109.5 degrees apart. And they do that to minimize the repulsion between things, okay? Now, for this molecule right here, the electron pair geometry is tetrahedral. And the molecular, I'm just going to use some shorthand here, guys, because otherwise we'll be here all day, okay, is tetrahedral. Do you guys know why this is called tetrahedral? Because if I connect the dots here, okay, in my mind, okay, so imagine these atoms here are all points. If I connect the points with a line, I make a shape that is a tetrahedron, which would have 4 equal faces, kind of like a 4-sided die. Huh? Yeah, but like triangles, right? So here's a triangle, on the back side's a triangle, on the bottom's a triangle, but they're all exactly the same. That is a regular tetrahedron. Crazy. It does. Okay, now let's take a look at distorted tetrahedrals. So you can have things that have a tetrahedral arrangement of electron pairs, but that have a different arrangement of atoms. A good example of the first distorted tetrahedral, which is called a trigonal pyramidal molecule. How many of you guys saw that last year? Yeah, okay, here's where it comes from. Let's take a look here at ammonia. Here is its Lewis structure. If I take a look at the central atom, how many effective pairs of electrons are around it? 4, right? We have 3 bonding pairs and 1 non-bonding pair of electrons. Because there are a total of 4 bonding pairs of electrons around the central atom, they want to be as far away from each other as they possibly can be. This is going to adopt a tetrahedral electron pair geometry, okay? So here's kind of like, okay, so here's my model. This was of methane, right? The difference is here, now in ammonia, it has 1 less atom that is bonded to it. But this electron pair is still there, right? It's the electron pairs that determine the shape of the molecule. This is still repelling these bonding pairs of electrons. They still want to be as far away from each other in space as they can, as they still spread out to adopt that tetrahedral arrangement of electrons. Does that make sense? Okay, so the electrons what determine the shape of the molecule. Okay, now if I ask you for the molecular geometry, that would be trigonal pyramidal. Okay. When you're looking at the molecular geometry, that is asking what shape do the atoms make. So it's kind of like I'm focusing just on the atoms. And you guys can see that if I do that, this looks kind of like a pyramid with a triangular base, right? That's why it's called a trigonal pyramidal arrangement of atoms. Does anybody have any questions about that? Tetrahedral arrangement of electrons. So if you just look at the sticks here, right? If I look at how these guys are arranged, it's a tetrahedral arrangement of the electrons. But you see there's not an atom up here that's bonded. So if I look at the arrangement of the atoms, which is what molecular geometry is, yeah, basically. Does that make sense, guys?
So why is the
Yeah, because they repel each other, they want to be as far away as possible. Now, I should point out that this idea, the valence shell electron pair repulsion theory, this is not physically accurate, right? Because are these electron pairs stuck here? No. The valence shell electron pair repulsion theory treats electron pairs like they are stationary, like they're not moving around. That is not physically accurate. But the reason we use this model is because it does allow us to accurately predict the shape of a molecule. Yes? That's a great question. Okay, you guys notice in the perfect tetrahedral geometry, like methane, what was the bond angle, guys? 109.5 degrees. Now, the reason you get that is because these bonding pairs of electrons all repel each other equally. Here there's a difference. In ammonia, we have that lone pair of electrons that is not used to form a chemical bond. The lone pair of electrons, it turns out, repels the bonding pairs more than the bonding pairs repel the lone pair. And here's the effect of that. Because this has greater repulsion, it pushes the bonding pairs away from it more and kind of squashes them together, and this bond angle you guys can see here gets reduced. It's 107.5 degrees here in ammonia, 2 degrees less than in the perfect tetrahedral shape. That's why I call these distorted tetrahedrals, because this is not a perfect tetrahedral angle. That make sense? Okay? Now, you don't have to memorize that this is 107.5 degrees. That is not something you have to know. But here's what you will have to be able to explain and articulate on the test and on the AP test. It is very likely that I will ask you, for a molecule like ammonia or some other distorted tetrahedral, predict whether the bond angle will be 109.5, greater than 109.5, or less than 109.5 degrees. And you will have to be able to explain to me that, well, I would expect this bond angle here to be less than 109.5 degrees because of the presence of this lone pair of electrons, which causes greater repulsion between itself and these bonding pairs of electrons, which kind of squishes and distorts that bond angle. You'd want to use more complex vocabulary than squishes the bond angle, okay, on the test, but that's the basic idea. Yes, Nicholas? Would it ever be greater than? No. Nope. Not going to happen. Okay. Let's look at another distorted tetrahedral geometry. Here's another example. Water. Here's the Lewis structure of good old dihydrogen monoxide, right? If I look at it, how many bonding pairs of electrons does it have? It has 2. How many non-bonding pairs? How many effective pairs total? 4, right? Okay. Because it has 4 effective pairs of electrons, the electron pair geometry for this guy is tetrahedral. Okay? But the molecular geometry, if we're looking just at how the atoms are arranged, this guy is bent. Okay? If you take a look at the model, here was my perfect tetrahedral, right? The difference is water has 2 less bonded atoms. So it has 4 pairs of electrons. These guys all repel each other. And so the electron pairs adopt a tetrahedral arrangement around the central atom. Okay? But the difference is we're missing these 2 bonded atoms. Oh, okay, never mind. Nothing. You woke up too soon, man. I was going to prank you. Never mind. Okay.
Oh, you think his phone was like in the thing?
No. I was going to slam his book. Whatever. Okay. Did he just like hit my classroom with a lawnmower or something? Okay. So anyway, what I was saying. So the electron pairs here in water adopt this tetrahedral electron pair arrangement. But you guys can see, if we look just at the atoms, that the shape they describe is kind of like this weird boomerang thing, right? This is a bent geometry. Okay? Do you guys understand the distinction? Okay. Now again, if we look here at water, it has 2 lone pairs of electrons. And if you look at its bond angle, how does that compare to the last 2 we looked at? It's even smaller. Because since it has 2 lone pairs of electrons, these guys cause greater repulsion than the bonding pairs of electrons. That compresses the bond angle even more. It squishes those guys even closer together. Okay? And so it's even smaller than for ammonia. Yeehaw.
So lone pairs will always have more repulsion than bonding pairs?
Always. Okay. Next, let's talk about things based on a trigonal bipyramidal electron pair geometry. Have you guys talked about this before? Nope. This is brand new. Okay? Now, you get a tetrahedral electron pair geometry if you have 4 effective pairs of electrons. You get a trigonal bipyramidal shape if you have 5 effective pairs of electrons. I'm going to build you guys a model here really quick. I will. Holy mackerel, could it be louder outside? Okay, so whoever's watching this podcast online, they're doing some kind of heavy yard work outside. Hopefully you guys can't hear that too loudly. Okay, here's my model of a trigonal bipyramidal molecule. Now the reason again they call this a trigonal bipyramidal molecule is because if you connect the atoms here with a line, this is the shape that it would describe in space. A pyramid on top, a pyramid on the bottom, each 6 triangular faces. Yeehaw. Okay? Now, let's look at an example of one such as this. A good example is PF5, phosphorus pentafluoride. If I was going to draw this Lewis structure, how many valence electrons do I have to do so? 35 from the fluorines, plus how many from the phosphorus? 5. So I'd have a total of 40 electrons to draw this baby. So I'm going to put my phosphorus here in the middle, bond to fluorine, 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 like that. Dot 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 dot. Okay? Notice here, guys, how many effective electron pairs does fluorine have? Or, sorry, phosphorus? 5, right? 1, 2, 3, 4, 5. So if I have 5 electron pairs around the central atom, that leads to a trigonal, bipyramidal electron pair geometry that is as far away from each other as they can possibly be. Now, here's what's kind of strange about this one. What do you guys notice about the bond angles? They're not all the same, okay? There's kind of like, this is sort of like 2 shapes like rolled into one. This is kind of strange, okay? If you guys take a look at it, this group of atoms here is called the axial group because if I spin it around, this is like an axis, right? Okay, now if you guys look at that bond angle, between these guys and these guys here in the middle, it's a 90-degree angle, okay? These guys here are called the equatorial group. And if you guys look, right, the maximum separation of space here is 120 degrees, okay? The reason why this happens is because if I have 5 electron pairs, this is the arrangement of electron pairs that gives the maximum separation of space and the least repulsion, okay? Does that make sense? Now, just like we had distorted tetrahedral geometries, I can have distorted trigonal bipyramidals if I have 5 electron pairs, but I'm missing 1 or more of the bonded atoms. Let's take a look at some of those guys, okay? Yeehaw! The first one is, that we'll look at here, an example is SF4, okay? I'm going to draw this guy's Lewis structure. If I'm drawing it for SF4, how many valence electrons do I have to work with? How many valence electrons? 34. I would have a total of 34 valence electrons to work with in drawing this structure. Sulfur is my central atom. I would draw a bond here to fluorine, a bond to fluorine, a bond to fluorine, and a bond to fluorine, like that. I'm going to put some electrons around them, like that. How many electrons do I have left to work with? I have 2 left to work with. Where do those go? On the central sulfur. Okay, now you guys can see that this guy, the sulfur in the middle, has 4 bonding pairs of electrons and 1 non-bonding pair. How many pairs total? 5. So it has a trigonal bipyramidal electron pair arrangement, okay? But you guys can see we're missing one of the atoms. So the electron pairs still adopt that trigonal bipyramidal geometry, but if I was going to describe the arrangement of the atoms in space, the shape is called seesaw. Because I'm not joking. I am not joking. Chemists have a weird sense of humor. For this guy right here, the electron geometry, I'm just going to say is trig bip, trigonal bipyramidal. The molecular is called seesaw. Okay? Now notice here, guys, how many bonding pairs do I have? 4. How many non-bonding? 1. If I have that sort of situation, I get a seesaw molecular geometry, yes.
Okay, so now I'm thinking, so the electron geometry is always the one with the first row, right?
Yeah, we'll talk about that. Yeah, we'll talk about that. Okay, then let's look at another one. How about ClF3, chlorine trifluoride, a bizarre molecule. How many valence electrons would we have total to build that structure? 28 electrons, okay? So we have my chlorine here in the middle, a bond to fluorine, and then bond to fluorine, and then bond to fluorine, like that. And we'll next try to fill the fluorines here with its valence electrons, like that. Okay, how many have we put down to do that? Yeah, 24. How many do we have left? 4 more. Those go on the central fluorine. Or sorry, chlorine there in the middle. Now notice, guys, we still have 5 pairs of electrons. We still have that trigonal bipyramidal arrangement of the electron pairs, but now we're missing one more atom like that. What shape is that? T-shaped. Yeehaw. Trigonal bipyramidal electron pair geometry, T-shaped molecular geometry. Nicholas Rosette.
Why can't it remove bonds from the active?
Because that leads to greater repulsion. This is the way that it happens to minimize the repulsion between electron pairs. Good question. Yes.
What shape is ozone?
What shape is that? Don't worry about it. Okay. But you can tell me later. Okay. It does not matter right now. Okay. So here's the thing. Also, okay, so I might ask you a question for something like this about bond angles, right? If we look back here at SF4, right, this is going to be a distorted geometry because this lone electron pair causes greater repulsion. If I asked you to predict what the bond angles are going to be, Luke Williams, what would this one be right there? Well, we don't know exactly what it'd be, right? But we know that it would be what? It'd be under 90, right? It'd be less than 90 because the bonds are distorted. We also know this bond angle here would be less than 120. We don't know exactly what it would be, but we know that it's going to be less than those because the lone electron pairs distort the angles. And this molecule here, it would be distorted even more because of the presence of the 2 lone pairs of electrons. One more, guys. The last distorted trigonal bipyramidal would be exemplified by xenon difluoride. If I draw the structure for xenon difluoride, I can just really quickly say that I'm going to have 22 electrons to build that structure. Xenon is going to be my central atom. I'll have a bond to fluorine and a bond to fluorine. I'll put my non-bonding electrons around the fluorine. And then I've got 6 left. Those go around the xenon. Craziness. How many electrons does xenon count here, guys? It's got a total of 10 valence electrons. Can it do that? Absolutely it can. Yes. Okay. Now if I look at the geometry here, I'm going to take off that last atom. Okay. It has 5 electron pairs around the central atom, so it adopts a trigonal bipyramidal electron pair geometry. The molecular geometry, though, how would you describe that? Linear. Ha 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 ha. Yes. So the electron pair geometry is going to be, again, trigonal bipyramidal. And the molecular geometry is going to be linear. I like it. What? Which one? What? This one?
Yeah.
This is T-shaped, yes. I just didn't write it down. That's T-shaped. Yeah. Okay. One more set of geometries. The last one, guys, we're going to look at are things that are octahedral. The reason they're called octahedral is because, I'm building you guys a model here, is because if you connect the dots, what you make is the shape of a regular octahedron. How many sides does an octahedron have? 8. Yeehaw. Okay? So if you guys take a look at this, if I connected the dots, okay, I would make a shape like this, a regular octahedron. Okay? I get an octahedral electron pair geometry if I have 6 pairs of electrons around the central atom. And the stereotypical example of an octahedral molecule is sulfur hexafluoride, which is SF6. My central atom here is sulfur. If I draw the molecule, here's the Lewis structure. I'm going to have a bond to fluorine, 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 bond to fluorine. And then I'm going to go dot, 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 dot. Yeah. Okay. Now, we didn't count up electrons here to begin with. Let's think just how many electrons I ought to have. Each fluorine brings how many to the party? 7, right? So 7 times 6 is 42. Sulfur's got 6, so the total is 48. If I look around here, right, each fluorine's got 8 electrons around it. I got 6 of them. That's 48. Okay, so it adds up. Yeehaw. So it's going to adopt this shape. There are 6 electron pairs around the central atom. If I look at bond angles, guys, how far separated in space are these electron pairs? 90 degrees, because if I have 6 electron pairs around the central atom, that is the angle that gives me maximum separation in 3 dimensions. Something like that. Yes. Okay. Does that make sense, guys? Okay, yes.
It's just for a T-shaped molecule, it will always be 90 degrees no matter what happens. Even though the lone pairs are there, it'll always be 90 degrees.
Well, yes, but it'll be distorted by the lone pairs of electrons. So it'll actually be less than 90.
Oh, it will be low.
It'll be less than 90, yes. Okay. What?
360 divided by 6 is not 90 degrees.
Whatever. Yeah, whatever, man. Whatever. Okay.
Nah, I'm just kidding.
I never claimed to be able to do basic math. I just said I know chemistry, man. I have a limited skill set. Snakes, chemistry. That's it. That's all I do. Okay. Now, just like distorted tetrahedrals and just like distorted trigonal bipyramidal geometries, there are also distorted octahedral geometries if we have 6 electron pairs but not 6 bonded atoms. Let's look at a couple. The first example is going to be bromine pentafluoride, BrF5. If I'm going to draw that Lewis structure, guys, how many valence electrons do I have to do so? $42. Yeah. So bromine is going to be my central atom. Bond to fluorine, 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 like that. Okay? Next, I'm going to try to fulfill their outer shell. So I'm going to go dot, 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 dot. How many electrons did I use? 40. How many have I got left? I've got 2 left. Candyman, wake up. I can see you're struggling. Okay. You should see my notes from college, man. I have a whole lot of those where it's just kind of like, you know, you can tell here I'm taking notes, and then it just kind of trails off as I fall asleep. It's pretty terrible. Okay. So I got 2 more to place. Those guys are going to go on the central bromine. Now, can you guys see that I've got 6 pairs of electrons on that bromine atom? Yes, but here's the thing. I am now missing one of those bonded atoms. So I have 6 electron pairs. The electron pairs want to be as far away from each other as possible. They adopt an octahedral electron pair geometry. But if I look at the shape defined just by the atoms, if I had to describe that, the molecular geometry, that is square pyramidal. Yes. And this molecule there happens to be because everything is like the same sort of kind of. Yeah. But for this guy right here, the electron pair geometry is octahedral. The molecular geometry would be called square pyramidal. And you'd ask Mr. Harper, do I have to commit this all to memory? And the answer to that question is absolutely. Okay. Yeehaw. Now, the last one we're going to look at here is xenon tetrafluoride, another xenon compound where xenon breaks the rules. I think you guys already drew this for homework, so I'll just do it here on the board here really quick. We got xenon, bond to fluorine, bond to fluorine, bond to fluorine, bond to fluorine, like that. And then dot, 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 like that. We have 4 more electrons that are going to be placed on the central xenon atom like that. Okay? So this is going to have, because there are 6 electron pairs around the central xenon, what is the electron pair geometry going to be? It is going to be octahedral. But if you guys take a look at this, right? If we're going to describe the arrangement of the atoms in space, that arrangement is called, because it's in a plane, it's flat, square, planar. Yes. Yeah. So the electron pair geometry, just for the people on the internet, is octahedral. The molecular geometry is square planar. Okay. Do you guys have any questions? Oh, yeah, there's like 2 more. Yeah, but we're not going to look at those. Okay, so if you guys look at your notes, there's this lovely, wonderful table that has all this stuff in there. This is amazing, this table, okay? And I want to just quickly describe to you guys how to use it. If you look in the first column, it says steric number. That's kind of a weird term. What this means is the number of effective pairs. Write this down. This is the number of effective electron pairs around the central atom, okay? If you look in the if you look in the next column, right, going down, so, and for 2 effective electron pairs, you get a linear geometry. For 3 effective electron pairs, you get a trigonal planar electron pair geometry. As you guys go across, this is showing the various distorted geometries. Okay? So for 4 electron pairs, what's the basic electron pair geometry? Tetrahedral. Then as you go across, you're showing the various distorted tetrahedral geometries, trigonal, pyramidal, and then bent. Then for 5 electron pairs, what is the basic shape? Trigonal bipyramidal. And then as you go across here, it's showing the different distorted geometries with increasing numbers of non-bonding electrons. Same thing for octahedral. This is all right here, guys. This is a lovely, wonderful table. Use it to assist you. The one on the far left, well, the one on the far left here is the basic geometry. This is going to be like for 6 electron pairs. Everything in this row will have an octahedral electron pair geometry. Well, whatever. This is like the, if you have 6 electron pairs, you get an octahedral electron pair geometry. If all the pairs are bonding pairs, the molecular geometry is octahedral. If one of the pairs is a non-bonding pair, you get a square planar. If 2 of the electron pairs are non-bonding, you get a square planar. If you have 3 electron pairs that are non-bonding, you get a T-shape.
So are they like the ones to the right are like subsets?
They're the distorted ones, yeah. And they're distorted because their bond angles are not going to be perfect. Okay. Ladies and gentlemen, we've got more time than we had in second period. We are going to do some examples. Yes. With your partner. Work out as many of these as you can.
We're not excited for example.
Oh no, I'm still going.
Shut up right now.
What?
Ask me a question about-
Bent.
Alright, so what shape is ozone?
Bent.
Oh, it's bent? Okay. So like because it's bent, and since like they're all like the same element, wouldn't electrons technically attract? Because you know how they like attract and bond with the same. It's not illegal to do it.
It is actually, but in California state law it is. All right, AP chemistry. Okay, really quick, couple I'd like to look at here really quick. Arsenic trifluoride. What's the electron pair geometry? This guy, the electron pair is tetrahedral. What's the molecular geometry? Trigonal pyramidal. Trigonal pyramidal, yes. 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 What about arsenic pentafluoride? What would that guy's electron pair geometry be? Trigonal bipyramidal. What about its molecular geometry? Same thing. Trigonal bipyramidal. IF3. What's the electron pair geometry? Trigonal bipyramidal. What's the molecular geometry? T-shape. Yeah. What about IF5? Octahedral electron pair geometry. What's the molecular geometry going to be, Kai?
Square pyramid?
Yes. Square pyramidal. Yeehaw. If you guys have questions about these, you should talk to me at lunch or something. But that is going to be it. Homework's on the board. Huh?
Are you going to be here after school?
Maybe.
You say you're like after school like Wednesday and then you teach.
Yeah, Wednesday I'll probably be here. I don't feel very good, but I'm going to probably stay.